Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Klepner and Kolenko. We will continue to discuss topics from Chapter 4, Work and Energy. In the last class, we were discussing about the application of work energy theorem, and as an example, we have seen that in the case of a uniform force or a constant force, the work done is path independent. It depends only on the endpoints. Today, let's see what is a case of another type of force known as a central force. Central force is a radial force which depends only on the distance from the origin, and it has the general form f of r cap, where f of r is a function of radius alone or function of distance alone. For example, if you look at the electrostatic force, which is proportional to the magnitude of the charges q1 and q2, and also inversely proportional to square of the separation distance. So this is q1 q2 by r square r cap. So this f of r, the scalar function of r, is nothing but q1 q2 by r square here. Okay. Similarly, if you look at the gravitational force, which is a g m e m by r square, where m is the mass of earth and small m is the mass of the object, once again you can see that for a given mass the force depends only on the separation distance. Just like for a given pair of charges in the case of electrostatic force, it depends only on the separation distance. Okay. Now let's find the work done by a central force F on a particle which moves from initial position Ra to final position Rb. For simplicity, let's consider only the planar motion. So as we have seen in the last class, we need to worry about only two coordinates, r and theta, and the displacement vector dr is given by dr r cap plus r d theta theta cap. So from work energy theorem, we know that WBA, work done in moving the particle from point A to B, is nothing but integral A to B f dot dr. Substitute for f and dr, you get integral A to B f of r dr. Now from this expression you can note that work is given by a simple integral over r, and since theta has disappeared from the problem, it's obvious that work depends only on the initial and final radial distances and not on the particular path. So just like the uniform force, in the case of central force also, the work integral is path independent. So in such cases where work depends only on the initial and final points or initial and final state, you can say that work is a state function. Now in which case or in which cases work becomes a path function or a path dependent function? One example is in the case of friction. Suppose you are in a square room and I ask you to push a table over the surface from corner A to corner C. Okay. Now you have two options, either to push it diagonally from A to C directly over path 1, or you can push the table by first moving to corner B, then moving to corner C. This is path 2. And you can easily notice that the amount of effort required for you to push the table is much less in the case of path 1 compared to path 2. So in other words, here when you push the table along the surface, the frictional force is acting against your motion. So you are working against the frictional force. Okay. And work done here is a path dependent function. So you have to utilize much more energy, or you have to put in more effort to make a motion along path 2 compared to path 1. This is because work integral in the case of frictional force is a path dependent function. It not only depends, it doesn't depend much on the endpoints, it depends entirely on the path, the specific path which is followed. Now if you think that the work done by friction in moving through the distance ds is dw, then you can write dw equal to minus f ds, where f is the magnitude of the friction force. The negative sign indicates that the force acts always against the motion. Now for simplicity, let's assume that f is constant. Then the work done by the friction in going from point RA to RB along some path is given by WBA equal to minus integral RA to RB f ds. F is a constant, you take it outside the integral. Integral RA to RB ds nothing but the total length of the path s fs. So the work done is minus f into s. So now you can notice for path 1 and path 2, the length of the path is different. That's why the work done is also different. So frictional force is one example where the work integral is no more a state function. This is strictly a path function. Having familiarized ourselves with the work energy theorem, it's now time to learn an important concept in mechanics known as potential energy. Now, we already know that work done by a conservative force on a particle as it moves from one point to another point depends only on the end point and not on the path between them. So for a conservative force, I can write the work integral as integral RA to RB f dot dr equal to a function of the endpoint RB minus function of the initial point RA. Right? This is the meaning of a state function. It depends only on the endpoints. Now the function of RB, I call it as minus u of RB. And function of RA, I call it as minus u of RA, where u of R is the potential energy function. We don't know what it physically means. For now, just take it as the potential function. So the work integral, I can rewrite it as integral RA to RB f dot dr equal to minus u of RB plus u of RA. From work energy theorem, I also know that the work integral is nothing but the change in potential energy, which is Kb minus Ka. So if I call minus u of Rb as minus ub and u of Ra as plus ua, then Kb minus Ka equal to minus ub plus ua. And if you rearrange the terms, basically you get all the A terms to the left hand side and all the B terms to the right hand side. Then you get Ka plus Ua equal to Kb plus Ub. So what's the meaning of is that the total kinetic energy plus potential energy at point A is same as total kinetic energy plus potential energy at point B. Now the choice of A and B are quite arbitrary. You can place them at anywhere. For example, you can put A at 5 cm, B at 10 cm, or A at 1000 cm, B at 10,000 cm, whatever. So irrespective of the choice of A and B, the sum of kinetic energy and potential energy has to remain a constant, which means this equation is true only if each side of the equation equals a constant, because the choice of Ra and Rb are arbitrary. So let's call this constant as capital E, which is nothing but the sum of kinetic energy and potential energy. There is another name to it. This is the total mechanical energy. So now my equation becomes Ka plus Ua equal to Kb plus Ub, which is equal to E, that is a constant. So this is a very important result. So we have shown that if the force is conservative, the total energy or the total mechanical energy is independent of the position of the particle. It remains a constant. In other words, if the force is conservative, the total mechanical energy is conserved. So we have derived an important principle known as conservation of energy from the work energy theorem. Now, one thing you have to particularly note is that whatever we have derived so far is not exactly the potential energy, but the change in potential energy. So if you look at the equation, UB minus UA equal to minus integral A to B F dot dr. So this, the left hand side is not potential energy as such, this is the change in potential energy. Because many a time in physics, the change in potential energy is more important than the actual potential energy. For example, if you want to find out the current flow between 2 points, the current flow depends on the change in electrical potential between those 2 points. So this is potential energy in terms of force, or you can also derive the converse relation, that is force in terms of potential energy, which you will do somewhere later during this course. I will just give you the expression. Force is going to be negative gradient of potential energy. Okay. Now, having defined the expression for potential energy, let's quickly calculate potential energy for some of the common forces, starting with a uniform force field. Okay. So we already know that for a uniform force, the work done is a path independent, and the expression is given by WBA equal to F naught dot RA minus RB. So you can see work done depends on the distance between the initial and final points, and not exactly on the shape of the path as such. Okay. Now, for instance, the force on a particle of mass m due to a uniform gravitational field is minus mgk. So here you are considering the z-axis as the vertical axis, and gravitational force always acts in the downward direction, negative direction. That's why you have the minus sign here. Now, for this force field, we can calculate what is the corresponding potential energy. So you are going to calculate the gravitational potential energy. Now imagine that particle moves from initial point RA to final point RB. Then, according to this equation, I can write the change in potential energy as UB minus UA equal to minus integral ZA to ZB minus mg dz. So here, as I said, z direction is the vertical direction. So when you do this integral and apply the limits, you get mg zb minus za. Now, once you find the change in potential energy, how can you find the potential energy at a particular point? One of the tricks is that you choose point A in such a way that the potential energy at point A is 0. Okay. So in this expression, if UA equal to 0, then the change in potential energy now reduces to potential energy at a point B. So this is how you calculate potential energy at a particular point. And many a time, potential energy is related to distance as 1 over R. So there is an inverse relation, which means when R increases, the potential energy decreases. So you can choose A at infinity. So at infinity, 1 over infinity is 0. So U of A equal to 0. So U of B equal to minus infinity to B F dot dr. This is one way of defining potential energy at a point. So physically, what does it mean? This is the work done in moving a particle from infinity to a given point against the force field. So this is the trick. You choose the reference point such that the potential at the reference point is 0. So that's what we are going to do now here. Let's choose the reference point ZA as the point on the surface of Earth, right? So you're starting the motion from the surface, and by convention, the potential on the surface or potential at Z equal to 0 is always taken as 0. Okay. Now imagine that h is the height above the ground. So at coordinate ZB, the height is h. Okay. So now your expression becomes UB minus UA, where UA equal to 0. So UB equal to mgzb. Now the height is h, so this is mgh. So This is the expression for gravitational potential energy. Potential energy at height h is mgh. Now, what is the advantage of this energy method over the Newton's laws which we have discussed in the previous chapter? In some cases, you can solve the problem pretty quickly using the energy method. Let's look at one such example. Suppose that a mass m is projected upward with initial velocity v0 equal to v0 xi cap plus v0 yj cap plus v0 zk cap. Find the speed at height h. Now, if you want to follow the energy method, we know that in the case of the gravitational force, which being a conservative force, the total energy is a constant. So if you take k0 and u0 as the initial kinetic and potential energies, and kh and uh are the kinetic and potential energies at height h, since the total mechanical energy is a constant, I can write k0 plus u0 equal to k of h plus u of h. K0 is half mv0 square. U0, since we start the motion from the surface of Earth, since height is 0, the potential energy is 0 from this expression. So this is equal to k of h, which is half mv of h square, plus u of h, which we know as mgh. So when you rearrange the terms, you get v of h equal to square root of v0 square minus 2gh. So using the energy method, you can quickly calculate what is the speed at height h. Now, in the case of uniform force field, you can also get the result by using Newton's equation, because force is a constant force. But the advantage with the energy method is that motion in all three directions is handled at once, because in this expression v0 square is nothing but v0 x square plus v0 y square plus v0 z square. So all the three coordinates are combined in a single expression here. On the other hand, if you were to solve the same problem using Newton's laws, then you will have to write the equation of motion for each components. You have three components, three equations of motion, then you have to solve them simultaneously. So by using the energy method, you can get rid of some of the mathematical difficulties in this case. Moving over to potential energy of the inverse square force, we now know that the central force or the inverse square force has a general expression F equal to F of R cap. So you can write the change in potential energy UB minus UA equal to negative integral RA to RB F dot dr. Substitute for F now, so expression become minus integral RA to RB F of R dr. Now typically an inverse square force or a central force has a general form A over R square. So if you look at the electrostatic force, that is 1 by 4 pi epsilon naught Q by R square. So for a given charge, 1 by 4 pi epsilon naught Q is a constant, which you call it as A. Or if you look at the gravitational force, which is gme by R square, so once again you have 1 over R square dependence here. So that's why we call it as an inverse square force. So this is the generic form. So instead of F of R in this integral, now I can write A over R square. Integral of 1 over R square is minus 1 by R. You apply the limits, you get UB minus UA equal to A over RB minus A over RA. Now to obtain a general potential energy function, instead of RB, I can call the general vector R. So U of R minus U of A equal to A over R minus A over RA. Now my aim is to find potential energy at a given point R. So you rearrange the terms, you get U of R equal to A over R plus U of A minus A over RA. Now look at the term inside the bracket. U of A is potential energy at a given point A, which is a constant. A is a constant, and for a given position, the position vector is also a constant. So this is A over R plus a constant C. Now this constant C has no physical meaning. We are free to give C any value we like, because as I said earlier, the choice of points A and B are quite arbitrary. So since you have the choice to give any value to C, the simplest choice is to make C equal to 0. So you have the expression in an inverse square field, or in a central force field, U of R equal to A of R. Now you can see, as the distance from the source increases, or as the distance from the center increases, you can see the potential energy is going to decrease, and finally at infinity you have potential energy being 0. So this is what I have said in the earlier case. You choose A in such a way that U of A equal to 0, and typically when potential energy has a 1 over R dependence, you choose point A at infinity. That's how you define potential energy as the work done in moving a particle from infinity to a given point against the force field. Okay. So if you look at potential and the field, both have a similar behavior. So if you take the case of an electrostatic field, it has 1 over R square dependence. So as you move away from the source, the field decreases. On the other hand, if you look at the potential, the electric potential, it also has a 1 over R dependence as depicted here. So just like the field, the potential also decreases as you move away from the source, and finally at infinity both the field as well as the potential become 0. Let's also discuss potential energy of another common type of force known as the linear restoring force or the spring force, because many a time we encounter this kind of force in physics problems. So consider a spring of equilibrium length R0 with one end attached to the origin. If the spring is stretched to a length R along the direction R cap, then it exerts a force F of R equal to minus K R minus R0 R cap, where R minus R0 is nothing but the displacement from the equilibrium position. So here you can see the force depends only on the coordinate R. So essentially this is a central force, and every central force is conservative. So this force is a conservative force. So I can apply the energy law here. So changing potential energy, U of R minus U of R0 equal to negative integral R0 to R F of R dr, which is minus K R minus R0 dr. So you apply the limits, you get half K R minus R0 square. Now by convention, the potential at equilibrium position is always taken as 0, because at equilibrium position the energy is minimum, so potential energy is taken as 0 here. So U of R0 equal to 0. So you get potential energy associated with the spring force as U of R equal to half K R minus R0 square. So this is the case of a single force acting on a system. If you have more than one force acting on the system, then the total potential energy is going to be the sum of potential energies of each individual forces. So that's for today. Thank you.